Thanks everyone for coming. Super excited. I didn't know much about CRaC before we had scheduled the meeting, so I went to read about it. So our speaker Gerrit, he works at Azul, Java champion, Java 1 rockstar. He writes in a bunch of different places. Very well-known and respected member of the Java community. So I'm very interested to learn about it and see how that, I don't know, it's different from JVM, CDS. So I'm very interested to know about it. Thank you very much. The stage is all yours.
Okay. Just waiting if the screen will disappear. Looks good. Okay. Yeah, cool to be here. It was on my list forever to visit New York in person again for a drug meeting, and it's so glad that I could make it this week. Yeah, the session is about CRaC, not the drug, but still I hope I can get you hooked on CRaC because it's really a really cool project. And it's coordinated restored checkpoint, and just to explain it shortly, if people have no idea what it means, is if you have a laptop and you close the lid, then it will shut down, right? And you open it again and it's just there. And this is exactly checkpoint and restore. So the operating system detects you shut it down, the lid, and then it saves the state to disk, and if you reopen it, it loads from disk back to memory. That's in principle the idea. And the question is how to do that on the JVM. But first of all, just short about me. My name is Gerrit, working for Azul Systems. We do JVMs. And other stuff, we also do Foo.j.io, so if you're interested in all things Java, we have a page, Foo.j.io, which means Friends of OpenJDK, but we couldn't say OpenJDK, so we had to use some techno. Everybody knows why. And I didn't know that we sponsor the jug, which is cool. Yeah, I did a lot of front-end stuff in the back, IoT back in the days, and now I'm working for Azul, and I'm glad to do something else, not only front-end. If you would like to have the slides, you will find them here, but I can also give it to Frank or Rodrigo, whatever, and then, because this is not the latest version, they are more or less up to date, but I update them all the time. All right, Java is great, okay? So we all know that. We have a vibrant community again, yes, that is very cool. People are meeting again in person. We have hundreds of Java user groups, and we have thousands of free open source software projects, which makes Java really awesome. But the real star of the whole thing is the Java virtual machine. Doesn't matter if you run Java, JRuby, Python, or Kotlin. So it's all the stuff's running on the JVM. The question is, how does it work? And I was a little bit surprised to realize that many developers have no idea how the JVM works. And it's okay to not know it, because if it works, it's fine. But still, sometimes it's good to know at least a few things. And I will try to give you a very easy introduction for one part of the JVM. So if you have a source code, which is in a Java file, and you put that in a JavaSIG compiler, then it will spit out a class file. Right, and this contains cross-platform bytecode, and if you have a JVM on your system, you can run this class file on the JVM normally. So then we take the class file and we use a so-called class loader, and this is very complex. The class loading itself, it could make a talk just about class loading, but here we just skip that and say the class loader loads the stuff into the JVM memory. And once it is in the JVM memory, it gets into the so-called execution engine. And this is just one word, but it has many parts. So we see already here 5 parts, and this is the interpreter. Then we have the C1 compiler, JIT compiler, formerly known as the client compiler. The C2 JIT compiler, formerly known as server compiler. Then there's the profile and the garbage collector. This is all the stuff that is in the execution engine, but we will only talk about the first 3 parts, because that is important to understand what CRaC does. So how it works is the interpreter takes the code line by line, from the class, from the memory, and then converts it into the instruction set of the CPU. And the JVM is watching that, profiling it, and counting method calls. So that means it really counts how often was this method called. And when this number reaches a threshold, then it will take this code and forward it to the C1 compiler. Right? And the C1 compiler, if it comes, the C1 compiler is the formerly known client compiler. and it is really fast compile, low optimization. That's the main idea. The reason for that is, as you can imagine, if you have a client app like IntelliJ, NetBeans, or Eclipse, it's our Java applications. If you double-click the icon, then you would like to start up the application as soon as possible. You don't want to wait until the compiler does the really best job and compiles it and optimizes it like hell, but you would like to see the application. That's the reason why this compiler compiles very fast with low optimization. That's the main idea. And once this code is running, the C1 compiled code, again the JVM is watching that code, that hot code, and counts how often this was called. And then it's another threshold. I think it's 10,000 times here. And once that happened and this threshold is reached, it takes this code and forwards it, including profile information, to the C2 compiler. The C2 compiler, formerly known as the server compiler, is much more complex, takes longer to compile and optimize the code, but the code that it produces is very high optimized and very fast. And the reason for that is, in the former days where the server compiler was built, it was made for stuff like the monolith, like an app server. And an app server you start up and it can take an hour, that's fine. It runs for a month, yeah? So that's okay. So startup time was not an issue with this compiler, but with the C1 compiler, it was made for startup time. Okay. So this whole thing is also called tiered compilation, because we have this combination. And this is in JDK, it came with JDK 7, but there you had to enable it. In JDK 8 it was default. From JDK 8 on we had this combined, both compilers in the JVM. And between this interpreter C1 and C2 compiler, we have different levels of execution. I don't want to go into the details here, because you can switch from 0 to level 3 to level 4. So there are different ways of transitions between these levels. But the standard is, first it gets interpreted, then level 3 C1 compiled code, and then C2 compiled code. This is usually how it works, if it's possible. Sometimes it's not possible. For example, if the queue for C2 is full, then you can't compile C2, then the code stays longer in C1, for example. Right? And then if there's free space in the queue, then it will go into C2. All these things can happen. But this is usually the way it works. And that leads me to the so-called execution cycle. This is in principle the same that I showed you before, just in one chart. And we start with interpretation here, which is slow, execution level 0. Then we have this profiling phase to find the hotspots. And then we take the code, put it into C1 compiler, which is fast, but really not high optimized. And then again, we profile this code. And then from there, it gets into the C2 compiler, which creates the very fast code. And then we see, oh, I don't have the, oh, you can't see it. And then you see this area over here. And this is, this I didn't mention before, this is de-optimization. The question is, why the heck do I need de-optimization? Because I do all this stuff to optimize the code. And then I de-optimize it, and you see the arrow goes back to interpretation here. The interesting part is, first of all, this is a performance hit, de-optimization. And the reason is totally clear, because we go from highly optimized code back to interpretation, and then again to C1, and then again to C2. The question is, why do we do that? Why is this needed? And the de-optimization, I just have a very simple example here. If this is my code block, it's just an if-then clause, and we just check if the value is greater than 0, then the result should be 3, otherwise it should be 0. That's the whole code. Now if the profiler figures out that this is the hot path, that means 99% of all cases, it's always, the value is always greater than 0. Then the compiler takes this whole block and creates this one. It just says result equals 0, equals 3. This is the, and you see there's not really a lot of code to execute. It really just says this value is now always 3. And it guards that inside the JVM. The value is still guarded, but this is not in the code anymore. And then what happens is, if I have a value equals 5, then it directly returns the result because it's set to 3. But let's say we have a value equals 0, suddenly this code is not valid anymore, and so that means the highly optimized code has to be thrown away, and this is the de-optimization. So that means in this case, this value equals 3, which was really fast code, has to go away, and then the whole block has to be again going to interpretation C1, C2 compile. Right? This is, and therefore you need de-optimization. You need a way to get back from the optimized code to the, let's say, interpreted code, and then again in this cycle. The reason for that is that the JIT is highly dynamic, so that means you have an application that is running, and when it's running, the profiler checks the behavior of the application. So that means the JIT adjusts to the behavior of the application. And in case it makes some suggestion and say, I think we go this way, because that looks like this is mainly the most used case, and optimize in that way, and suddenly the other one happens, then it has to de-optimize and do it again for the whole code. That's the main idea. And that makes it so powerful, because the application behavior can change, and so the JIT can optimize the code and can follow the application. Okay, that's all great, but yeah, it takes some time. It's not for free. And I tried to come up with a little chart, because if you talk to people, then you hear these days often JVM startup. The JVM is so slow, Java is so slow, we can't use it in microservices. Yeah, okay, it might be, but you have to really ask yourself, what is slow? If you just take a JVM and you take one class, and in that class you just do the main method and you say system out println hello world, compile that and tell me it's slow. It's blazingly fast, and this is in principle the JVM. What makes the startup slow is your application code. Because usually what we define as JVM startup is the time to first response of your application. And if you have an application that loads lots of classes and have huge amount of dependencies, then you can imagine that all this stuff has been loaded, interpreted, compiled, and it takes time before your application can respond. And this is the JVM startup. So it depends first of all on the code that you use, right? If you have no code, then there's nothing to optimize, and then it's fast. If you have a lot of stuff, then it takes longer. And then there's this other thing that people sometimes mess up. It's application warm-up. And that means, I said, startup is time to first response. Doesn't mean that at that point the application is at high performance. It just means your application, the first time you get an answer from your application. And then it starts to optimize, right? So that means caches will be warmed up, and you apply some workload to your application. So and the compilers will optimize the code more and more. And then at one point you reach 100% performance. It's at full speed. Let's say you have a high-speed trading application, then usually you have to warm it up until you get really to the full performance of the application. And this is application warm-up, and that takes some time, and people sometimes mess that up in JVM startup and application startup and JVM warm-up, so it's a little bit tricky. I just would like to make that clear. Okay. If we take a look at a JVM performance graph, then we see here three colors, and the yellow one in the lower left, this is the interpretation phase. And you see it's really short. It's in the 100 milliseconds range usually. And this means every code that goes through this and then quickly comes into the C1 compiler. This is the green area here. And that contains the compilation and profiling. And then it gets into the blue, which is the C2 compiler. And there you see this ramp where the performance ramps up. That takes some time, right? And then we define this, for example, as a JVM startup, which is not really correct here, but because here we are already at 100% performance, right? So the time to first response would be earlier in that chart. But if we define it like that, then we see these gaps here, this periodic gaps, and this is usually garbage collector pauses, because if you have a stop-the-world garbage collection, then you see these trenches here. But this is not de-optimization. This is de-optimization. That means we see code, and it was already fast, and suddenly we see a huge gap. And that means that there was some behavior that was not really taken into account by the compiler, and the code was not optimized for that. So it had to throw away the code and start again, and that leads to these gaps. And you would like to avoid that, of course, right? If the application is running and suddenly everything's fast and whoop, you have to wait for 2 seconds and then, oh, there it is again. You don't want to see that. In some applications, doesn't matter, but if you have applications where you need really performance and responsiveness, then you don't want to see that. That means we would like to go there, right, where the garbage collection works. There we would like to be at the high performance. Okay. So, if we take this knowledge, question?
Yeah, it was on the previous slide. I wanted to
Okay.
ask while it's still handy. Do de-optimizations only happen during the startup part, or can they happen?
Most of them happen during the startup part, but as soon as the code is compiled completely and the behavior of the application, or let's say you apply a workload to it, the standard workload, then at some point all code is compiled and optimized, and then you won't have de-optimizations. But if you load code at runtime, then it could change, right? Because you can do that in Java, at runtime you can load additional code. That means this code has to go again through all these phases, and that could lead to de-optimizations in other parts. So it can happen at runtime, but usually not.
Thank you.
Okay, then if we take this knowledge now to microservice environments, then we have to do that at the first run, and we have to do it at the second run, and the third run. And so every time we have this startup problem, this ramp up, right? And that sucks. Because that's the stuff that people talk about. It's so slow, right? If you work with AWS Lambdas, for example, they suffer really a lot from startup time. Because it's just a little bit they have to do, but to do that, they have to start up the JVM every time. And this is not so good. So the question is, wouldn't it be great if we can do something like that? So we warm it up first, and then from that moment on, the next time we start, it's full performance, and we stay there. That would be great. So the question is, do we have solutions that help us here in this case? First of all, there's class data sharing, CDS. Someone asked me for that already. And I didn't have that in my slides until I gave the presentation in Poland, and then directly before my session was a session about CDS. And I talked to the speaker, and then he said, oh, yeah, this is cool, CRaC. And then I said, well, this is also cool. So we both exchanged knowledge, and now he has parts of CRaC in his slides, and I have CDS here. This is class data sharing, and there's app and dynamic CDS available. And in principle, is a dump of internal class representations into a file. This will be, you can imagine, if you have to load the class loader, has to load all the classes, and they could be wherever on the class path. That takes time. If you have a lot of dependencies, a lot of classes, you have to load all of them. Just imagine you take all this information, dump it in one file, and then load it just from there. So the class loader doesn't have to search everything. That really improves startup time, and this is in principle what it does. And for those who doesn't know CDS, never heard of it, don't worry, it's per default enabled since JDK 12. So that means if you have JDK 17, CDS is already enabled. But you can tune it. So that means it's enabled, but you can even make it faster. And there is no optimization or hotspot detection here. This is really class loading performance that will be improved. And yeah, like I said, it only reduces the class loading time. And there is a session, and this you can get up to 2 seconds faster. And there is a session and also a blog post. And this is the guy that I was talking about, NYJavaSIG. And you will find his blog here and at that link. And it's quite interesting. He goes into all the details, how you can tune up the app CDS so that you can really gain up to 2 seconds. And that's quite interesting to see. Okay, but it really didn't help us with this ramp up. That was really before that. You see, it happens at the class loading time. Then it's JVM memory, then is the compiled interpretation. So it doesn't help us here. Nice idea, but doesn't help. Then we have ahead of time compilation. This, I guess everybody knows that. And then always have to ask, is someone using GraalVM native image here? Nobody. Played around with it. Yeah, okay. Okay, yeah, it's interesting because everybody's talking about GraalVM native image, but when you ask people, then it's no, we don't use it. So some people tried, but didn't really work. There are reasons for that. So that you don't have to interpret bytecode if you use AOT, and you don't have to analyze hotspots if it's plain AOT. And there is no runtime compilation of code, and it starts at full speed straight away, which is great. And GraalVM native image does exactly that. So that means problem solved, right? Not so fast. So IoT is by definition static. That means you have the code, you put it into the compiler, and that creates a native executable out of it, and that's it. So that means the compiler it will compile the code before it is run, and that means the compiler has no idea what the code is really doing here, right? So I just talk about AOT because there are also differences. because if you use profile-guided optimization, then you can do all these things that I told you that are not possible. And what is PGO? So if you have, let's say we have GraalVM native image, then GraalVM also comes with a JIT compiler. So what it does is you run the code once and compile it with the JIT compiler and profile it. And then you take that profile information and apply it when you create the native image. That's the main idea. This is PGO. And that's all cool. And if we take a look again at the JVM performance graph, and this is not hard numbers, this is something that you find if you read a little bit about it, then it says AOT compiled code without any optimization can get up to 60–65% of the JIT code. And it's totally clear because the compiler has no idea what's going on, right? It just compiles the code into native and then it runs. It starts up fast, but the performance of the code is not good because it's really not highly optimized. It's just compiled the code to native. If you use PGO, you can reach up to 90% of the JIT. That's possible. And you have to keep in mind, you have to create the profile first. And the second thing is the profile that you create is one snapshot. That means if you exactly know your workload, then you can use that. If you have dynamic code, then it might be optimized for one situation, but it doesn't mean it's always good. So this is really still, the code is like a static blob, and that's it. It won't change anymore. Once it is compiled into native, that's it. Right? Just to keep that in mind. I tried to do a little AOT versus JIT, which is not so easy because it depends on the language and on the application and all that. But in principle, you can say that AOT can't really use the same amount of method inlining because they can only do it upfront, where the JIT can use that aggressively even at runtime. You load code dynamically, it can be optimized. This is not possible with AOT. You can't load at runtime. This is not a code. It's not possible. Runtime bytecode generation also not possible with using AOT. With the JIT, it's no problem. Reflection is the biggest pain point, and this is one of the reasons why so many people don't use GraalVM native image in production, because the AOT code needs to know all the classes that are used, everything. So it needs to know the whole world to run. With a JIT, don't need that. You can, it's dynamic, right? So you can load stuff at runtime. It will optimize it and compile it. AOT, that doesn't work. Right? It needs to know everything upfront. You can't use speculative optimization. This is something like branch prediction. So if the JVM is really smart, so it really tries to figure out this code looks like that it would like to do this, so I optimize it in that way. Right? This can go wrong, then we can de-optimize, so that this is the reason when you might have de-optimizations at runtime, but it's rare, but at least it's possible, where the AOT can't use that, because they compile it once, and then that's it. So either it's right or it's wrong. But the overall performance is typically lower when you use AOT compared to the JIT. But the biggest pain point that I see here is if you use AOT native image, then the deployed environment is totally different from the development environment. So we are used as Java developers to take the IDE, we code everything there, we run the tests in the IDE, we pass it to the CI/CD system that does the build, all the tests are green, and then you create the native image. And what happens then is that native code is not JIT compiled code. And it's really completely different sometimes. Even if how variables are handled in native could be different. And that leads to strange effects. So I had one guy came to me after my presentation and said, can I use that in production, the CRaC stuff? And I said, nah, not at the moment, but you can try it. And he said, oh man, that's so great. Can I use reflection? Yes, you can. And I asked him, what's the problem? And he said, yeah, we run it in production, we try to. And all the tests are green. We have code coverage of 90%, which is great. But as soon as we create the native image, it breaks. It just fails. And we can't debug it, because it's native code. You can't use the normal tools. There are other tools to do that. But it's not that easy. So this is one of the pain points that I see. Where in Java, you can debug the Java code. It's all closed in Java, right? So we can use that. But if you mix native with Java, that's not so easy. It reminds me a little bit on GWT in the past. You use Java and create JavaScript. And then suddenly you have to debug JavaScript. But you coded Java, right? And this is the same. You code Java and you create something native C or whatever is down there. And then you have to debug that one, which is tricky. Okay, it's not everything's bad, right? So the native image starts really fast. That's because it's just native code. And we don't have any overhead when we compile it at runtime. This is where the JIT has this overhead, where we have to compile the code and at the same time it's running. That means your code is running and in the background it will be optimized and compiled. That needs more memory also, right? So that means the memory footprint is also larger in JIT than in AOT. Because the AOT native image just compiles only the stuff that is needed, because it knows all classes that will be used. Where the JIT, if you load a library, and then in this library you just use one class, the whole library will be in your code. That means the memory footprint is larger. Okay, so that means the JIT disadvantages are mainly, it requires more time to start up, the CPU overhead to compile code at runtime is there, and we have a larger memory footprint. So this is, compared to AOT, the biggest pain points for the JIT. Let's take a look at the different approach here. And this is called CRaC. Someone ever heard about that? It's interesting, because it's not really that new. It's called Checkpoint Restore in User Space, and it's a Linux project, and it is part of the kernel since 2013, so that's nearly 10 years already in the kernel. And it was made to freeze a running container or application, and then save the state of this this so-called checkpoint to the disk, and then at a later point in time you restore from that checkpoint back into memory. The stuff that I told you, closing the lid and reopen it. And it's only available in Linux, so there's no CRaC on Windows and also not on Mac. And there are reasons for that. And it's already integrated or will be used by OpenJDK, by Linux containers, Docker and Podman. They use all CRaC. Not every time, but you can enable that, so you can use it. Some use that all the time, and in others you can enable it. Okay. It's mainly implemented in user space. The main goal is migration of containers for microservices, and it heavily relies on the proc file system. Why I mentioned that is there are Linux distributions they don't use proc, and then you can't use CRaC. Right? So you just have to keep that in mind. Usually, all the stuff that we usually know, all the Debian derivatives, they all use proc and others too, so it should be there. You can just search on your Linux box for CRaC. It's also a command line, so you can find that. If you find the command, it's there. So pretty easy. And you can even use it on the command line, so it means you can checkpoint an application and also restore it using CRaC. And it can checkpoint lots of things like processes and threads, application memory, memory map files, shared memory, open files, pipes, FIFOs, sockets, interprocess communication channels, timers and signals, and it can rebuild a TCP connection from one side only, so no handshaking needed. It's quite impressive what this project can achieve. And there are others, so we not only rely on CRaC, we could also use any other project or library, and there are others, but CRaC is the most used one, and I would say it's more or less bulletproof because it's in there for 9 years and really in good shape. But it does come without, nothing comes without challenges, and so also CRaC. And you can imagine if you create the checkpoint and then take the files to another machine and try to restore it there, you might run into problems, right? It might be environment variables, it might be shared memory or open files, so you can't just take the files from one machine, go to the other and restore. This might work sometimes, but it doesn't have to. And the other thing is if you would like to restart the checkpoint multiple times, it doesn't work because we have in Linux, we have this PID, the process ID, which is unique. And this is part of the checkpoint. That means you can't really restore it more than once. And yes, if you guess, wait a minute, if the PID is already taken by whatever process, can I restore it? No, you can't. We are working on something to make that happen, but at the moment it would crash if the PID is taken. If you run it in containers, that's not a big of a deal, because usually then it's the first process you start, it has PID number 1, so this is not really the problem. The bigger problem is the JVM here. First of all, you might think, well, you said CRaC was made to checkpoint an application and restore it, and the JVM is an application, so that should work. And I agree, it should work, and if you just have the plain JVM, it will work. The problem is your application that is running within the JVM, that has the problem. Because you can imagine, I have the JVM, I have my application running, the application has a file open and a database connection open. So now I checkpoint it using CReO from the command line. It will checkpoint the JVM, it will stop it, you save the files, you restore it, the JVM will start, the application will try to continue and will figure out that the file is not open, the database is not there, and it will crash. That means you can't really do that easily because your application has resources everywhere open and that has to be closed and reopened, so you can't just shut it down and assume that the application will just pick it up again, right? This is the problem. And that leads me to CRaC, which means coordinated restore at checkpoint. And the big part here is the coordinated. The coordinated should fix the problems with the applications. That's the main idea. And CReO comes in a specific version that we patch bundled with the JDK. So that means we have a JDK, and with this JDK, we bundle CReO in a specific version that makes it possible to run here. And what it does, it cleans the heap and it compacts it, in principle the same that you do when you do a garbage collection. So that means the JVM is in a safe state. And then it can also throw checkpoint exceptions. So if you do if you miss something, then it will tell you, wait a minute, you forgot to do this or that. Right? So it won't let you alone in the dark. So that's quite helpful. And it comes with a pretty simple API. I will explain that in a minute. And it can create checkpoints either using code or JCommand. And this is the ways you do it. And people often ask, okay, but if I have multi-threaded code, so how can you make sure that everything's shut down correctly? Because we use the JVM safe point mechanism. This is exactly the stuff that is used for garbage collection forces. And I think nobody of you ever coded something like, oh, if there is a garbage collection, then shut down this thread, and then that thread. You don't have to do that. The JVM can do that on its own, and we use the same mechanism here. Right? So it's no problem with that. The whole thing is an OpenJDK project. That means even if I work for Azul and it's led by us, so Anton Kozlov, who's one of our engineers, he's the lead engineer of that project, we provided that code to the OpenJDK project. You can find it here, openjdk.org/projects/CRaC. And that doesn't mean it will make it into OpenJDK, because this is not our decision, but there's this red big company that you might know, and they make the decisions here, and they might say, well, it's not available on Windows and Mac, so sorry, you can't do it. We also provide a library that fixes this problem and makes it at least possible that if you use that library, and I will give you a link to the repository, then it will handle the case that you run it on Windows, for example, then it will figure out the JVM it's running on, does it support CRaC or not? And if it's not supporting CRaC, it will give you dummy interfaces. They just return nothing, just don't work. But it won't break in the IDE, so you won't get exceptions or something else, or something like I can't find this class or something like that. And this will fix the problems on Windows and Mac. It means you can develop on Windows and Mac, but if you run it then on a Linux box that has CRaC in the JVM, it will work. Right? So we provide that too. So that might be the workaround that is needed to make it into the official OpenJDK version sometime in the future. Okay, I told you already the coordinated in CRaC is we need to make the application aware that it gets checkpointed, and also when we restore it, we have to let the application know that it was restored. Right? This is the important part. Because otherwise we run into problems that I told you, like the open files or sockets, right, that won't work when you just check on JVM. And to use that, we have two command line parameters with -XX colored checkpoint 2 equals path. And the path is in principle just a folder. And we pass the parameter to the JVM, and in case there's a checkpoint, the JVM knows where to store the checkpoint. That's the main reason. And if you would like to restore from that checkpoint, you just give the JVM the other parameter in the -XX called CRaC restore from, and you point it to the path, and then the JVM will figure out, oh, there's a checkpoint, and restore the checkpoint back to memory. That's the two commands that we added at the command line. And the API, which is really pretty simple, it just comes with one interface, and it's called resource. And it has only two methods, before checkpoint and after restore. And that means you have to implement this interface into every class that makes use of resources. That sounds like a terrible idea. Like, oh my God, I have to change the whole code base. No, you don't have to, because it usually means everything where you have sockets open. That could be database connections over the internet or whatever. There you need it. If you have open files, you need it. And that's more or less it. If you have sockets and open files, this is the biggest pain points where you need to implement the interface. And if you are honest, then you will figure out, okay, this is not so many places. It should be possible. And we still talk about microservices. And there's a reason why it's called microservice. So it shouldn't be a macro service, right? That means even in a microservice, it shouldn't be that many areas where you have to implement the interface. And once you do that, then we need another mechanism to let the JVM know this is a resource. Notify the resource in case there's a checkpoint or there was a restore, right? Okay. And to do that, we have a so-called context. And this context, you have to register your resources into that context to let the JVM know. And you can get the context by calling core.getGlobalContext. Right? This is a static call, and it's just one context in the whole JVM. And there you can register your resources. And if you register them in this context, then they will be notified. That's the main idea. The idea is so you implement the interface, you get the context, and then you register your resource into that context. Right? So this is the idea. Then there's another thing. If you have resources that depend on each other, which might happen, it doesn't have to, but it could be possible. That means you open the database, for example, this is the first thing you open in your application. That means that's the first resource. And then you have other resources that use the database, which could be possible. Then if we shut it down, we have to make sure that we shut, or let's say if we call the before check-one methods, we have to make sure to call them in the right order. And the context will do that. So that means when you register the resources in the context, this order, the context will keep that order. If you do the before checkpoint, it will call the methods in the reverse order, and in the after restore, it will do it in the same order you did that the first time, to make sure everything is in the right place. And I have a demo that shows that. And if you do the checkpoint from the code base, you can call core.checkpointRestore, and it will create a checkpoint. And at the moment, this is not really useful because it will shut down the JVM when you create a checkpoint. But we have a solution since Tuesday that makes it possible to get the JVM running. So it means you can create a checkpoint and then the JVM will just continue running. At the moment, it will still shut it down because we have to create a next build first. And if you do it from the outside, then you use jcommand. And I also show you how to do that. So I have a very simple example. It should just give you an idea, and it should remind you on the JVM startup, this ramp up stuff. So it's a scheduled thread, and that will be executed every 5 seconds, and it will call a loop, and in that loop I create random numbers from 1 to 100,000. And then I will take this number and put it into a method and check if this number is a prime. And to make it more realistic, I use a cache, because we cache everything, right? So we have a cache, and it will check is the result in the cache. If no, or if yes, then I return directly the result. This is pretty fast because I don't have to calculate anything. And if it's no, then I have to calculate if it's prime. If it's a large number, it takes longer, so that is just to make the code slower. That's the main idea here. And then I get the result, I store it in the cache, and then I return it, so that is the slow loop, and the other one is fast. And then to make it more realistic, the cache has timeouts. Because if you have a cache, then usually you don't want to keep the stuff in the cache forever, so they time out and then you wipe it out of the cache. So this one will start after 50 seconds, and every 10 seconds it will just check if there are values older than 10 seconds, and then we'll just wipe them out of the cache. Okay? That means the first run should be pretty slow, because no number was calculated yet, and everything has to be put in the cache. So that means the first run is slow, and then with each iteration it should be faster and faster, because the cache gets filled up, and that means if the cache is completely filled, it gets all the results from the cache, which is really fast. And then I did some tests, and this was the performance, how it behaved, and you see it's similar to the JVM startup time. So that was the main reason, to give you an idea what it is. And this one was at 9 iterations, it reached more or less the optimal performance here. And then you see it goes up and down and up and down. This is because the cache remove stuff, add stuff, and so on. So, but this is what you see if you have an application, you have never a flat line. It's always like going up and down. And then usually it turns out to be around one number. Right? Okay, and now I have a demo. And the demo I do in slides first to give you a little bit of a background. So we have a shell window on the left side, and we have a shell window on the right side. And I just start my jar file with the parameter CRaC checkpoint 2, and I point it to the CRaC -files folder. So there should be the place where it should store the checkpoint. Then I start it, and it will give me the PID, and then I have some system out print lines to show you how I registered the classes. First the generic cache, and then the main, and then the first run took 27 seconds, so really slow. And because the cache was not really filled. After the run, it was to 63% was filled in the cache. Then the second run, 10 seconds, and then it gets faster and faster and faster over time. And at one point, it's fast like here, and then we say, okay, now it's fast enough, now let's create a checkpoint at that point in time. So I go to the second shell and execute J command with the name of my jar file, and then with the command jdk.checkpoint. This is the new command that we added. You can also use the PID, you don't have to use the jar file name, right? So the PID would also work. And when we do that, it will create the checkpoint, and before that it will call the method before checkpoint in main and in generic cache. You see the order is reversed now in this case. And then it will create the checkpoint, and then the JVM will be killed today. So with the next version we can change that, and it can keep running. So that means it's killed now, the checkpoint was created, it says it was successfully executed. If I wait no more than 10 seconds, what would you expect? What would happen the first time I started? Because the cache, I told you, will forget values that are older than 10 seconds. And exactly what you guess, if I start it now and I don't take that into account, it will wipe out all values from the cache and will start from the beginning. So it will be slow again. And the reason for that is that if you have time-dependent data in the checkpoint, it doesn't. You have to take care about that. So what I did in the before checkpoint method, I created a variable, and in that variable I just stored the current epoch milliseconds. And because the variable is part of the checkpoint, that means when I restore it, I can just read out my stored variable. I know when was the checkpoint, and I can just get the current epoch milliseconds. I calculate the delta, and I apply the delta to all values in the cache. And then the cache is up to date again. Right? So that's what I did to make it work. Because when I restore it, this is then the JVM warmup in this case, because I warmed up the cache, right? This is not really startup. And when I restore it, I just call java minus and then point it to the CRaC files folder, and then it will start, and you see it's directly there. 23 milliseconds, the cache was completely filled, and it just continues running. It also, you see that it counts from 12, so it continues counting. It's really like you stop the JVM and then you just start it from that point, from that checkpoint. And like I said, you have to, if you have time-dependent data, you have to take care of that. It's your job to do that. The question is, if you experience the problem that, oh, do I need, like, let's say like this, you have to think about if you have to checkpoint every container or every microservice. It's not needed for everything, especially if you have something like a cache. You don't want to checkpoint a cache usually, but especially if it has timeouts, or if you have session timeouts, you don't want to put them in a checkpoint. The next time you start it, everything's timed out. Right? So this stuff you have to keep in mind when if you should play around with CRaC. Because you can run into trouble, and then you will wonder, the performance is not that good, and then usually this is the case, that you have something that is time dependent. It could also be state that is time dependent, right? It could be an indirect dependency on time, so you really have to think about it. Okay, I told you can create the checkpoint using J command, either with a jar file or with a PID, or you use it from code, then it's called checkpoint restore. Checkpoint restore is a little bit misleading here because we just do the checkpoint, right? So it's not really doing a restore. So it's you might going to change that in the future, but at the moment this is the name. So the question is when to checkpoint, when to create a checkpoint. That's the critical question. So I can just give you an advice what we do when we create the demos is we apply a typical workload to our application. This is not always possible, I know, but sometimes you have that, or you have tests. Tests are a good thing to warm up the JVM. And then there's a parameter, a command line parameter called -wx plus print compilation. And what it does, it prints out all the compilations. That means if you do that, and you start your application, you see on the screens like, it just scrolls like hell, because every compilation will be shown. The good thing is, at one point it will get less and less compilations, because everything's compiled. So that means if you see it gets less optimizations going on, or compilations going on, so if they are ramped down, then that might be a good point in time to create a checkpoint. And we are working on a solution to make that accessible in the JVM. So we are working on something a mechanism that you can just ask the JVM, is it now a good time to create a checkpoint? Because we can figure out, is everything compiled, right? And this is not so easy because it really depends on your code. But we are trying to find a way to make that easier to figure out when is a good time for a checkpoint. Then you create the checkpoint and you're good to go. The next question is, what is a typical use case? First of all, the idea is to use it in microservices. You don't want to checkpoint an application server. Right? You can, probably, but I don't know what the use case should be to checkpoint an application server. So that means if we talk about microservices, then usually we talk about containerized applications. And it makes sense. So what you do, you run the application in a Docker container, for example, then you create the checkpoint in that container. And then you have to commit the state of this checkpointed container, because we need the files of the checkpoint in the container. You commit the state of that container to another image, and then you start from this checkpointed container. That's the main idea. I'm working on an example at the moment using GitHub Actions, which should make more easy for people to understand the whole workflow, because this could be a little bit tricky how to do that correctly. The problem is that we have to, it's easy to create the container and run the code and then create the checkpoint, but then we need to save this state somehow. And this is a little bit tricky, but there will be something. A few words about compatibility. I already told you this is only on Linux, and it's only Linux x64 at the moment, and the OpenJDK version that we provide is 17.02 at the moment. And it would be possible to create an ARM64 version, but we don't do that at the moment because we just have enough to do with this stuff. But in principle it would be possible to do that, and it might follow in the future. And then there are a few words about so-called upgrade and downgrade. The JVM is really smart. So it doesn't only optimize or compile code for a specific CPU, but it really does that also for the CPU family. That means if you have a Core i7 and you have a Core i9, for example, that's two different CPUs that are more or less the same family, not really, but as a user you won't see the difference, but the JVM knows the difference. So it compiles code differently for different CPUs. Even if it's a Core i7 step 4 or step 10, code could be different. And what I mean with upgrade is if I create the checkpoint on a Core i7 machine, I can run that on a Core i9. They are backwards compatible, that works. But the way around doesn't work. So that means I can't create something on a Core i9 and then expect that to run on a Core i3, for example. That won't work. Right? So we have to keep that in mind. And I tell you that because if you run that in a cloud environment, then you can set up first of all, if you use Docker, it works then on Linux, Mac, and Windows. We tried that, so that's possible. As long as the architecture of the CPU is the same. You can't run, for example, and this is the reason why I have my old x64 Mac with me, because we only have x64, and on my ARM or my M1 Mac, I can't run that. It's not possible. And the same goes for Linux, Mac, and Windows, so you can't really run a Docker container that was made for x64 on ARM64. But if you have a cloud environment, and let's say you have Azure, and you have something like it's called node groups, and if you define a node group, then Azure makes sure that this node group always has the same CPU architecture. So if you have Core i7 in one node, then all the nodes have this Core i7 with the same stepping. It's the same thing. But if you create a Kubernetes cluster, you can run different node groups in one cluster. So if you would like to make use of CRaC, you have to make sure that all the node groups in your Kubernetes cluster are the same CPU types. Otherwise, it can crash. Right? So this is just to make you aware of that. So it has a lot of positive effects, but of course there are some things you have to take care about. Okay, so the demo that I showed you, and I will show it also running, it's available on my private GitHub account. I just make it available because you can download the OpenJDK, you can fork that project and can directly play around with it, right? So you can try and play in the IDE, you can add your own stuff. It's very simple, just 4 classes, but it gives you an idea and makes starting easier. And now I showed you, we patched the OpenJDK and provided that for the OpenJDK project. That's cool, right? Azul did that, and I'm from Azul. I did my demo, and it's also cool. The question is, how good is it really? Right? Of course, we did tests with other frameworks. So we made some tests with Spring Boot, Micronaut, Quarkus, and we also did some XML transform. And this is the time to first operation. So Spring Boot took 3.9 seconds. Micronaut was around 1 second, Quarkus 980 milliseconds, and this XML transform stuff took 4.3 seconds. This is running on an OpenJDK, plain OpenJDK. With CRaC, that was the startup time. And that's quite impressive because this is in the range of native image that JVM provides. But this is still the JVM. So you have all the goods from the JVM, but you have the startup time like a native image. And you stay in the Java world. You don't have to go into native. So you might ask yourself, how is it possible that we have a startup time of 3.9 seconds or 4.3 and then suddenly it's in the same range as the others? Well, the reason is, this mainly is because we have to compile classes and optimize it, right? Once that is done, the code is fast. The checkpoint is just loading from I/O. So we only rely on I/O here. And hard drives are fast, so that means it's just really loading from the SSD back into memory. And that's the reason why it's more or less the same speed for all of these. The differences are definitely if you have a lot of resources that you have to reopen or re-establish, that might take a little bit longer. Right? So, of course, but even establishing sockets or database connections is not in the range of seconds usually, it's milliseconds. So we are still faster than starting on plain OpenJDK. All right, so the summary is, CRaC is a way to pause and restore JVM-based application. It doesn't require a closed world as with native image, where it means you need to know everything, but here we don't need to know that. And we have a potentially extremely fast startup time, full performance level. It eliminates the need for hotspot identification, method compiles, and de-optimizations, because we do that after all that happened. So I told you that the whole optimization phase, after that we create the checkpoint. And then we don't have to identify hotspots and stuff, right? Usually not. We have improved throughput from the start. It's an OpenJDK project, and it can also save you some infrastructure costs. So the question is, how can it save infrastructure costs? If probably most of you know this kind of chart. We have a CPU utilization on the y-axis and then the time on the x-axis, and we have this peak in the beginning. And this peak is the JVM startup time. This is everybody's complaining about. And that's the problem if you run it in cloud environments. And what companies do, they spend a lot of money using a large amount of CPUs to make this as fast as possible, just to overcome this first peak, right? Now if you use CRaC, you have the interpretation and compilation overhead here, but you create the checkpoint there, and then you can run from there. That means you don't need that much amount of nodes anymore, and that can save a lot amount of money if you do that. So it eliminates the startup time and the CPU overhead. Still, the JVM memory footprint is larger than with the native imaging runtime, but usually memory is not a big deal. The CPU cores, that's the expensive part if we talk about nodes in the cloud. All right. All the code is available on github.com/CRaC. You will also find the OpenJDK builds there. You will find the demos there with Micronaut and the Quarkus stuff and Spring Boot. Everything we did. There's also a demo for Lambdas, for AWS Lambdas. If you would like to play around with that, we have also a demo for that. So you can just check it out. There's a wiki page on openjdk.org. It doesn't really contain a lot of information, so it's more information in the GitHub repository that I showed you. And now we come to the best part of the documentation. It's all right. So what I do here, I have 3 shell windows. It's a little bit dark, but this in the center, it will start a Docker container, and in that Docker container it will start my application, the same one that I showed you. And because it takes so long, I actually started already. And you see, okay, the startup time of the JVM itself was 97 milliseconds, by the way. So just for the people that say JVM startup is slow, because you can measure that with a JMax speed. So JVM startup itself is not really slow. But then I told you it's 27, and this one is 28 seconds for the first run until the cache is filled up. And on my M1 Mac, it's 1 second to do that, just to give you an idea how fast these things are. And then it will be, now we see 28 seconds, now it's I think 11 and then 4, and then it gets faster and faster. But if you imagine this is your service and you run that, and you don't really want to wait 28 seconds before the first response of your application is there, right? That really sucks. And then it's faster. Now every 5 seconds it will do that, and the cache is filled. Okay, that's fine. So if we can do the same, but now I started from the checkpoint in the Docker container, and then it's like this. Here we go, it's running full speed. And I can start it another time on another. And you see, it's directly fast. The cache is fully filled, and the first response was like this. And this is the same if you have a, whatever, Quarkus or Micronaut application, doesn't really matter. So the startup time is really fast because it just loads the stuff from the files back into memory. And now if I stop it and just start it again, you will see it will just start again from the same point. It doesn't matter. Because it just loads the stuff from these files back into memory. The question that might come now is, okay, how big are the files? For this demo, it was 30 megabytes, roughly. That's the checkpoint. And that's mainly the heap, right? Because we compact that, and then somewhere we have to store that. And it's the same as a heap dump. You can think about that. It's also not really readable code, so there's no source code or something that you can read. There's not any additional security we apply to that. So it's in principle the same, like I said, as if you do a heap dump. That's more or less what it does. The good thing by using Creo is this is on operating system level. And if you use off-heap memory in the JVM, sometimes people do that, we can checkpoint that. So that means off-heap memory will be checkpointed and restored because it's bound to the Linux process ID. And everything that's related to that ID will be checkpointed by Creo. So, and with this I'm done. And I think we have a couple of minutes for questions, if there are any.
Yeah, 2 questions.
Yes.
In this demo, it says 18 milliseconds, but then there is a pause, and it says second run, next run.
Yeah, because, I exactly know what you mean. This is because what I do is, I told you in my program, every 5 seconds it executes the loop. But the first start was like this, right? It directly started running, and then it took 5 seconds to the next run, 5 seconds. This is the reason why we see that gap. Okay. Here it was faster than this one. We saw at the beginning it took forever. That's the scheduled thread executor has all the threads and they are waiting, and then suddenly when it has time, and then it starts with the 5 second thing. Right? They are just running in the background. That's the reason why it's a little bit strange. Yeah.
Guys,
Second question.
Second question is, it might sound strange, but did you consider command line tools and checkpoints? Like, Gradle created Gradle daemon and Maven created Maven daemon. But in theory, could they have gone with CRaC instead?
You know what? I was at a conference in Chicago 3 weeks ago, and the guy from Gradle came to me and said, this is really interesting, and maybe we can use that for Gradle. Because they saw that and were like, that could be really the solution. So they are looking into it. A lot of different people and companies looking into it. AWS, the guy from Corello is the JDK from Amazon. They saw that, and this is cool. And I don't know really if but it looks like they are playing around with it for the lambdas, and they can do because they own the cloud and they own the JDK. So whatever they do in the JDK, they don't care, right? So yeah, Corello might get that too. And there's also Red Hat is playing around with it, and Quarkus already has support, and Micronaut also has support for it. So that means that Micronaut is the best right now. They have out-of-the-box support. It's a module, you can just activate it, and then you don't have to even add or implement the interface. You just have an annotation and say this is a resource, and then Micronaut will take care about closing and reopen all the resources for you. Spring Boot, the demo that I showed you, this is a hack. Because in Spring Boot, what we did, we patched Tomcat and then pointed Spring Boot and said, this is now your embedded web server. Right? So because in Spring Boot, I don't know if they will ever do that. Unfortunately, because this is so widespread. Yeah, but there are ways to use it. But like I said, this is an ongoing project. It's not ready yet for production. But definitely, I would really hope that someone will, you can play around with it. If you figure out problems, you can find issues in the GitHub repository. Even if you have questions, just post them there. Or if you have specific use cases or whatever, because we just see it from our point of view. But the interesting part is you, because you are really running your applications and you have the problems that we try to solve. And if we don't know the problems, we can't solve them. So if you have issues, then just post them on the GitHub repo, please. Any other question? If not, then I'm out.
Yeah.